Hi kids, welcome to our lesson on complex zeros. So last year you should have done some preliminary work with complex numbers, right? Learning how to add, subtract, multiply them, how to get rid of I in your denominator if necessary. And we did a little bit of finding non-real zeros last year by long division or by synthetic division. So there's really not too much new here. Just to remind you of the fundamental theorem of algebra, which you had last year as well. A polynomial of degree n has n complex zeros. Now remember, complex zeros include the numbers that, right? The complex set of numbers is the union of the real and the non-real, right? So every real and non-real, so every number you've ever dealt with is a complex number, right? You just didn't know it, and you didn't need to call it a complex number. For instance, complex numbers are of the form a plus or minus bi, where a and b are both elements of the real numbers. So when you have the number 2, that is a real number, but it is also a complex number because I can just write it like that. Okay. Furthermore, a non-real number, like the square root of -2, is not a real number, but you were taught last year that you can write that as I root 2, right? Suck the negative out as an I, suck your eyes out, right? I root 2. I root 2 is strictly a non-real number, but it's also complex. Change colors here. The square root of -2 is not real. We write it like this, right? And this is not a real number, but it is a complex number because I can write it as 0 plus I root 2, right? Complex number. Any non-real number can be written as a complex number. Any real number can be written as a complex number, right? So when I say complex zeros, that includes all the zeros that you've already dealt with. But we are going to now include the non-real zeros. So a polynomial of degree 3 has n complex zeros. Some of them, maybe 3 of them are real, maybe 1 of them is real, and 2 are not real. Don't forget that zeros may be repeated. Excuse me. The linear factorization theorem means that you can always factor a polynomial. So in Algebra 1, we learned that we called, sometimes you would say, oh, I can't factor this quadratic. But what you meant was you can't factor it nicely. You could use the quadratic formula and generate the irrational zeros, which are still real. And then we taught you how to turn those into factors. But then there were some that we just said, oh, I can't factor at all. But what we meant was it was prime. We didn't mean there weren't zeros. Don't forget about your leading coefficient. A polynomial can always be expressed as its leading coefficient or its dilation factor times a list of products. And those products are linear. Coefficient on x is 1. The exponent on x is 1, and every number here is a 0 of the function or an x-intercept if the 0 is real, and just a 0 still, a 0 is also an x-intercept if the 0 is a real number. So complex conjugate zeros. Remember, complex conjugate. Conjugate means pairs. So you've been dealing with conjugates for a long time. For example, x minus 5 and x plus 5 are conjugates because when you multiply them together, there's a nice little pattern in that the two middle terms cancel out. Complex conjugates are zeros that are not real that always come in pairs. If a polynomial, which has real coefficients, so A, B, and C, right, or all the coefficients of the x squared, the linear term, and the constant are all real numbers, which is all we're going to be dealing with, and A or B are real numbers, then if somebody tells you 2 plus 3i is a 0, it must be so that 2 minus 3i is also a 0. So non-real zeros always come in pairs, right? That's the lesson learned here. Non-real zeros of polynomial function always come in pairs. And they're conjugate pairs. So notice I am just asking you to multiply here. This is going to be a quadratic, right? And x to the first times an x to the first is a quadratic. The zeros of this quadratic are not real. And they are 1 plus or minus 3i. So 1 plus and minus 3i are zeros, which means plugging in 1 plus or minus 3i for x will give me 0. But this is asking me to multiply it out. These are the linear factors. And my goal is to multiply. So I want to get rid of parentheses. So let's multiply. X times x is x squared. X times negative something is negative x times that something. Now I'll go the other way. X times negative something is negative x times that something. Then lastly, negative something times negative something is positive. Okay, now let's clean it up. So last year you studied this pattern, and you should have known that complex conjugates follow our conjugate pattern. You get a squared minus bi squared, but last year you learned that I squared was -1, so this is a squared plus b squared. So I don't actually have to FOIL this out. I know I'm going to get 1 squared plus 3 squared, which is 10, right? 1 plus 9, which is 10. Then I'm going to have x squared here minus x plus 3ix minus x minus 3ix. And notice that my i's went bye-bye here. There was no i's after I multiplied here because of my conjugate pattern. And then here, bye-bye to the i's simply because of multiplication. So I ended up with x squared minus 2x plus 10. A nice quadratic whose y-intercept is up here at 0, 10, and looks something like that. No x-intercepts because there were no real zeros, right? So here, notice the form of the non-real zeros, right? Notice I'm taking this exact same problem, but replacing 1 and 3 with a and b. Notice what happened in the abstract when I multiplied them out. And if all you have to do is change these numbers and see the pattern over and over again. So much of mathematics is pattern recognition. I always got the first term squared, and then I got the conjugate pattern. In the middle, the i's canceled out, and I was left with a double of that. There's my pattern. If I multiply a quadratic with only non-real zeros out, there's my pattern. Right? So if I could have looked up here from the beginning, if I worked, now I don't, if you came up to me when I hadn't, second semester and said, what was that pattern again or whatever, I'd say, ugh, right? I don't use this pattern enough for it to be really, really familiar and in the front of my mind, but I can always just multiply, right? But if I used it over and over and over again, I would look at this and I'd say, oh, that's going to be x squared. Here's my a. So I'm going to be minus ax doubled plus the complex conjugate pattern. Woohoo! A quadratic that has real coefficients, which notice this does have real coefficients, right? The coefficients are 1, -2, and 10. Yes, 10 is a coefficient technically of the x to the 0 term. If it has no real zeros, we call it irreducible over the reals. We call that prime, okay? Because it is prime over the real numbers. We also further identify prime as having factors that have, if you can be reduced over the reals, but the coefficients aren't rational, we still call that prime. Every polynomial with real coefficients can be written as a product of linear factors and irreducible quadratic. And within that quadratic, you have real coefficients also. That is always true. And so you have to really look at the directions. What am I being asked for? Am I being asked to factor, right? Linear factors. If I want all the linear factors, that includes the non-real ones. But if I am just asked for linear factors and irreducible quadratic, I just need to go as far as I can in the set of real numbers. So the first example we're going to do here, look at the directions. Find the zeros. I would have to tell you that I want you to include non-reals, right? But we're in that section because I'm dealing with complex zeros, which means real and non-real. Right? So first they said complex zeros, which means both the real and the non-real, right? My set that I'm working with has been expanded to the set of complex, and they want me to find all of the zeros and then write f of x in terms of, which means equals, its linear factors. And remember, linear factors are always of this form. 1x to the first minus the 0. Okay? So to do this problem, step 1, I need the rational root theorem to tell me what are all my possible rational roots. Right, so I need the factors of 8 and the factors of 1. So those are all my possible rational roots. So I'm going to start with them, and then I have to plug each one of them in. And which ones, plug them all in and see who gives me 0. Now, sometimes you can be a little smart about this, right? Plus and minus 1 is a possibility, isn't it? Try those first. Try easy ones, get it? First ones, get it? So let me try f of 1. What is f of 1? 1 minus 3 minus 5 plus 5, oh, those go away, minus 6 plus 8. So what do I have here? 1 minus 3 is negative 2. Negative 2 minus 6 is negative 8. Negative 8 plus 8 is 0. Yes. Step 2 then is to start dividing to get the rest. I'm sorry, step 3. So take the 0 you just found and divide. I think I'm going to use synthetic division here. So what did I do? I took an x to the 5th and I reduced it to an x to the 4th, right? This is an x to the 4th. You have to divide until you have depressed the polynomial to a quadratic. So how many more times do I divide? I started with an x to the 5th, so this is an x to the 4th. So I have to keep going, right? So what do I have to do? I have to go back to my step 1 and pick another number. Now I'm going to give you the numbers, okay? In the interest of time, I'm going to give you the next factors. 4 is a factor. So what have I reduced to? I started with an x to the 5th. This was an x to the 5th. I resulted with an x to the 4th. I divided by a linear factor. So what is this? This is an x cubed, right? I'm going to give you, so what I would do for real is I would go back to my P over Q list and I would plug and chug again. But I'm going to tell you that negative 2 is another 0. And now I've depressed to a quadratic. So this is x squared plus 0x plus 1. That is an irreducible quadratic over the reals, right? I can picture that in my head. That's a quadratic that opens up and has a y-intercept of 0, 1. So once I've depressed to a quadratic, I either factor it if it's a nice quadratic, or I use the quadratic formula. Actually, I don't even need the quadratic formula with this one. I mean, I could use it, but why wouldn't I just do this? X squared plus 1, I want to know what makes it equal to 0. X squared is equal to negative 1. That is not solvable over the reals. But how many things can you square and get negative 1? Well, that's plus and minus I. Right? So I now have a list of factors. And my list of factors is, from step 2, I got 1. with a remainder 0, divided by 4, and I got a remainder of 0, divided by -2, and I got a remainder of 0, and then solve this quadratic, which if it had 3 terms, I would have used the quadratic formula, but the only 4 terms, I just used my skills from last year. And how many factors is that? 1, 2, 3, 4, 5. 5. Right? Now your job, but I'm not done, because the job, it asked me to express f of x in terms of its linear factors. So I have the factors. I'm sorry. Oh, I used the wrong word there. This is my list of zeros, excuse me. So now for my factors, f of x is equal to the dilation factor, 1, times, I didn't do a very good job with my space management here. So I'm going to write them out like this. Put your zeros into linear factor form. Guess what would happen if I asked you to multiply that out? You would start with the complex ones, and you would get x squared plus 1. And then you would start multiplying, and you'd get all of these polynomials until you ended up with f of x. Crazy. Multiplication undoes division. Division undoes multiplication. All right, so in class, we'll do another one of these together, okay? These are long problems. They're worth an awful lot of points. And if you don't do enough of them to increase your speed, you won't finish an assessment. You do have to work on speed. All right, let's do some division with complex numbers. So I modeled so to remind you what synthetic division looked like, but the answer to this is why not? Right? Why not? So what if I want you to verify that 1 minus 2i divides this 4th degree polynomial? Now think about a 4th degree polynomial with a positive leading coefficient, especially with a y-intercept of positive 65. It is possible that this 4th degree polynomial, which has 4 zeros, it is possible that none of them are real. But notice I gave you the word verify. Verify means that I am giving you that 1 minus 2i is a 0. 2i is a 0. And then I'm like, ah. Now, I could plug 1 minus 2i here and raise it to the 4th. I could plug 1 minus 2i here and square it. I could put 1 minus 2i here and multiply it times 14. And then I could do all that algebra and combine it and see that I get 0. But that would be a little bit of a dagger, but how about I use the fact that if I divide and get a remainder of 0, that's the same thing as plugging in to show that I get a 0, right? Crazy, whack, funky. So let's do the exact same process. Notice I took the 0, 1 minus 2i, and then I put the coefficients. Hey, don't forget, for synthetic division, you must put every coefficient. There is an x cubed there. What's its coefficient? Yep. Don't forget that. All right, so I'm going to bring down the 4. And I'm going to multiply 1 minus 2i times 4. Well, that's simple. That's 4 minus 8i, right? And I'm going to put it above here. But now what do I have to do? Now I have to multiply 1 minus 2i times 4 minus 8i. This is why you did this objective last year, and you're assessed on it. You know how to multiply 1 minus 2i times 4 minus 8i. You can do that quickly and easily because you took Algebra 1, so you know how to FOIL, and you took algebra 2 where you did the foiling with complex numbers. And I did that multiplication. I'm not going to go over it here, but you can do it. And I got negative 12 minus 16i. Now I forgot to write something down here. Sorry. Got kind of ahead of myself. I had to add these together. 0 and 4 minus 8i is 4 minus 8i. And that's what I had to multiply by. 1 minus 2i times 4 minus 8i. And that's what I did up here. And I got negative 12 minus 16i. And now I have to add, right? This is really plus 0i, right? That's what I mean about a real number is actually a complex number. So 17 and negative 12 is 5. 0i and negative 16i is negative 16i. Now what do you have to do? You have to multiply that times 1 minus 2i. So now I'm going to take 1 minus 2i and I'm going to multiply it by 5 minus 16i. You can do that because you oh, it is already blue. Sorry. You can do that because you took algebra 1 and algebra 2. And what you got when you were done was negative 27 minus 26i. Don't forget that 14 is a complex number. It is 14 plus 0i. So I added 14 and negative 27, and I got negative 13. 0 and negative 26i is negative 26i. And now I have to multiply 1 minus 2i times negative 13 minus 26i. And when I multiplied those two non-real numbers, I actually got a real number back. Just like complex conjugates, right? Anytime you multiply complex conjugates, which are both non-real numbers, you get a real number back. So what I did this time too, it just happened to work out. If you don't believe me, do the actual multiplication yourself. And when I did it, shockingly enough, I got negative 65. And when I added that down, I got 0. Therefore, since I divided this fourth degree polynomial by 1 minus 2i and the remainder is 0, therefore 1 minus 2i is a factor of f of x. One of the factors. And as a matter of fact, I've also, because 1 minus 2i is a factor, who else is a factor? So the other two zeros are either also complex conjugates or they are real. But that's not what they asked me to do. They just asked me to verify that I do divide, right? 2 divides 10 because when I divide, I get 5 with a remainder of 0. 1 minus 2i divides this fourth degree polynomial because when I did division, I got a remainder of 0. Swell. All right. We will see you next time. Have a good one.